we can't do, right? So here's a sponge, I think from the Pacific, a basket sponge. Joanna Eisenberg's now, she's at Bell Labs, she's now at Harvard. And this thing's about 10 centimeters long, and it's a glass basket with very interesting mechanical properties that grows itself. Write down the genetic program that produces this. Don't know. And here's another thing we can't do. This is from the architecture department at MIT. They would like to grow houses, right? So gigantic gourds that grow and differentiate into a 4-bedroom, 2-bath house. So there's a lot of room for biohacking in the future. Now, to contrast this with other engineering disciplines, here I'll use civil engineering. Here's a project from around here, France, where folks over a period of time constructed this artifact, this viaduct, this bridge. And so the thing that's interesting as a would-be engineer of biology is, how come the civil engineers get to make stuff like this, yet all I get to do is, sort of add a photoreceptor to E. coli? And so the way to think about this for me is to look at how the civil engineers got to this point, because they started here thousands of years ago at the beginning of the Stone Age, when they recognized, we recognized that rocks are useful. Right? You can build walls, but the rocks you find in nature are hard to work with because they're all different. And so let's start making regular rocks with standard interfaces so that it's easier to build stuff. And even though the basic building blocks become simpler, the artifacts we can make from them become more complicated, like flying buttresses and so on. And so it's easier to make bridges and you name it. Now later on in the Stone Age that we live in today, that we inherit, people have already become dissatisfied with rocks. And so we grind up the rocks and we make new